Hi, I'm Matt Turk, and I am honored to introduce Dr. Katy Huff, Dr. Catherine Huff. Dr. Huff is currently a data science fellow at BIDS, the Berkeley Institute for Data Science. She did her undergrad at University of Chicago and her graduate work at University of Wisconsin-Madison, and spent some time at Argonne. She's a computational scientist, a nuclear engineer, and she has a huge number of accomplishments and achievements, including founding the Hacker Within, which is an organization that now has a local chapter. She is an early adopter and influencer in the space of software carpentry, and is now on the board of the Software Carpentry Foundation and the steering committee or the advisory board for Data Carpentry, its sibling organization. Katy is also the author of a book called Effective Computation in Physics, which can be found at physics.codes, utilizing the new top-level domains recently allowed on the internet in a clever way. And she's also awesome. She presented at WISPY 2.1 at SciPy and is a longtime member of the scientific Python community, along with any number of things. So I'm just totally honored to be the one to get to introduce Katy so that some of her glory can reflect back on me as I'm up here talking about her. So anyway, Katy, please.
Thank you, Matt. Thank you so much, Matt. That was very sweet. And almost all of it was true. So I am, as Matt said, Katy Huff, and I'm going to be talking about scientific computing education. So I'm actually a nuclear engineer, and I do a lot of computational nuclear engineering research, and I'm not going to talk about that at all today. I'm going to talk about something else that I care deeply about, and I actually almost never have a chance to talk about it in a formal academic setting, so it'll be really fun, I think, for all of us. Some of it many of you already know, and I'm going to give you some cool examples of inspirational solutions to a problem I think you're all deeply aware of, and I'm going to give you some insight into a project I've been working on in this space. And let's just start with who I am. I'll just briefly go through that. So as Matt said, I went to the University of Chicago and got a physics degree in undergrad. I went to the University of Wisconsin to get a nuclear engineering degree, a PhD. And I'm now at the University of California, Berkeley, which is a beautiful place. And I am a postdoc in both the nuclear engineering department and the Berkeley Institute for Data Science. In that time, I worked on a great number of projects. My graduate work was focused on a fuel cycle simulation code called Cyclus, which is an agent-based model for tracking nuclear fuel through the industrial nuclear fuel cycle. But I'm not gonna talk about that. And I have also done some interesting work with computational analysis of accident transients in a high-temperature reactor, and that's resulted in a piece of software called PERC, which analyzes reactor kinetics in Python. But I'm also not going to talk about that. I've also contributed to an excellent toolkit for nuclear engineering in Python called Pine, which a number of people here in the audience are aware of because it has a relationship with YT. But I'm not going to talk about that either. My funding comes from the Fluoride Salt-Cooled High-Temperature Reactor Project, as well as the Berkeley Institute for Data Science and the Nuclear Science and Security Consortium. I spend a lot of time working on SciPy every year, but I'm also not going to talk about that. The things that I am going to talk about, as Matt sort of indicated, are a project called the Hacker Within, a community called the Hacker Within that now has a space here, in fact, directly related to NCSA, software carpentry, and a book that I wrote and a course that I and my co-author and some colleagues are building around that book. So this whole talk is related to a problem that I think is a grand challenge in science today. And ultimately, I think all of you will agree with this statement that if scientific curriculum in the university were a program, an algorithm perhaps, for preparing students to do real research once they graduate, it's a software that needs to be refactored pretty heavily. It hasn't kept up with the times in a lot of ways. And a lot of you are at the forefront and are very odd creatures because you have made it. You've gotten to the place where you've taught yourself enough software skills and scientific computing knowledge to do well as researchers in this current environment where computing is so essential to science. But not all students that leave either undergraduate or graduate school are really prepared to be the researchers that they need to be, particularly in the early career stages of their research, given the amount of computing that's necessary today. So I'll just give you a couple of ideas that you will definitely agree with, and then there will be a pop quiz, and then I'll tell you some cool things. Okay. So science. It's supposed to build and organize knowledge, right? And it's supposed to test explanations about the universe, and it's supposed to do so systematically, objectively, transparently, and reproducibly. You have a number of people working on making sure science does that well here in NCSA. And they would all agree, and I'm sure many of you would agree, that if it's not all of these things, it is not science, right? And in fact, computers should be making it easier to make science that way. Victoria Stodden is a great example of someone at the forefront of sharing this idea. She is one of your professors here at NCSA. And computers should help us get science to that point by improving our efficiency, reducing our human error, automating the things that we don't want to do, right? Computers are way better at repeating tasks than humans are. We start to fall off in our performance at the end of a series of mundane tasks. However, computers continue chugging along because they don't have a loved one to go out to the movies with later. They are good at repeating those tasks. You're good at going out to the movies. So they should automate the mundane, simplify the complex, and accelerate research. A place like NCSA is where that happens. And people come to a place like NCSA with their scientific problems and want to use computers to do their science in this way, but they often don't have the skills. And they don't use computers effectively enough to do the science that we need to do as reproducibly and objectively and transparently. And efficiency is lost because they're not using computers in the way that they could. And a lot of this is related to what education really needs to be doing. So education's purpose, and I'll just give you this, maybe you have other definitions of education, but I think it needs to transfer knowledge, you know? And historically, that used to happen because there was a dearth of information and access to information. One might go to an island in Italy to learn to be a glassblower because that's where the information was, right? But now the information is everywhere. So it's not exactly about transferring, information as much as knowledge now. It needs to communicate concepts and convey, in particular, how to think. A lot of people from liberal arts universities have been saying this for a very long time, but this is also true in science, technology, engineering, mathematics type fields where, we need calculus to help us think in a calculus-driven way about our science. And it has to, therefore, also prepare learners for their futures. Some of those futures might be in industry or in the national labs or in universities, but almost all people who are going to undergraduate degrees in science want to do something that relies on that skill set when they leave. And when they go to graduate schools in science after that, they also want to be capable of doing the research that's expected of them. And we are actually not doing this as well because computers have changed everything. So I mentioned the ubiquity of information in the world right now. But something else to keep in mind that I'm sure all of you are acutely aware of is that undergrads today, and in fact, many early graduate students, don't remember a time without the internet. I'm just barely old enough to remember a time without the internet, barely. And those people have a strong notion of how to find information, right? And they have no problem networking ideas, considering collaboration in a distributed global way, a thing of today. It's super easy for them to imagine that they could go online and make friends with someone they've never met and edit a paper together, perhaps with a whole group of people they've never met, whereas some of us are facing that possibility for the very first time, collaborating on a paper together with people across the world in different time zones, and conveying how to think needs to incorporate the kind of computational thinking that students are starting to need when they go on in their lives. Program. So how many of you did not program? Okay, cool. No shame. So how many of you learned from a course, a specific course to program? All right, okay. There are a lot of CS people here. So how many of you learned from a book? Okay, some subset of the people who just raised their hands about the course learned from a book. How many of you taught yourselves to program? Okay, now everyone is also raising their hands. So can you pick one? No. So the reason for that is actually closely related to the fact that it's a combination. And a lot of the things that you do are going to be incorporated into your courses, but also related to your goals. Another question here is, so here's the second question. Why did you learn to program? So your options are, I don't program. I learned to complete a course assignment, or I learned to program to complete some non-scientific project, or I learned to complete a scientific project, like in a research context, okay, or something else. So first question, you don't have to raise your hand if you didn't learn to program, but that's one. There's a couple of you, we've already covered that. How many of you learned to program to complete an assignment in a course? Okay, like 10 of you maybe. Okay. How many of you learned to program to complete some non-scientific project? Yeah, so a bunch of you were like hacking at home to do something fun, right? How many of you learned to program in order to do research in a scientific project of some kind? Okay, so a whole bunch of you. I'd say that's like maybe the majority, but still kind of closely related to the hackers in the house. So that's actually really common, and that's because scientific curriculum doesn't include as much of the scientific computing that it could, and a lot of people show up to a project and then need to learn to program in order to do that project. And so that's one of the things that I think is somewhat wrong with the way that we currently teach science. How many of you are computer scientists? Actually, so you have CS degrees. Not many. All right, how many of you would describe yourself as scientists? Yeah, okay, almost everyone. So many people in science find themselves at a scientific project without the skills they need to complete it. And when I was a graduate student at the University of Wisconsin, my PhD advisor wanted his students to help one another to learn those kinds of skills. And so we created this we created this group called the Hacker Within, which is a group that Aaron, do you want to raise your hand real quick? Aaron Anderson here has actually started a chapter of here in Illinois, and it's a peer learning group. And we had this great dream. It was a bunch of grad students, right? We had this great dream of leading each other towards scientific computing best practices, things that we had heard about that might help our ability to do the kinds of work as computational nuclear engineers and other folks from other disciplines that we needed to do to get our theses written. So this peer-led organization had meetings. It was sort of like a self-help group for lost graduate students, okay? And the way that it works is that you gather together and you talk about something cool and potentially useful. So the general format, this is a picture of us meeting in Berkeley. And you can see it's sort of a round table. People jump in and say things that are interesting to them, but primarily one person will lead a 40-minute demo of things that they think are important. Like here we're talking about the file system hierarchy standard actually in the bash shell so that people can learn to find things on their Unix-like operating systems. But then it's followed by lightning talks related to people's particular problems in science. So someone can get up without any particular warning or registration and say, I'm having a problem, I'm an ecologist, I have this population model, and I cannot figure out how to design the data structure to hold everything. Anyone have any ideas? or they say like, hey, I just figured out how to automate Python syntax highlighting in my text editor. Really stuff that is basic and fundamental to general software development, but absolutely never taught to graduate students in the sciences. And so they can share these kinds of skills, become much more efficient, and make friends. The University of Wisconsin has a chapter. Obviously, it was where it was started in 2009, 2008. When I moved to Berkeley, I started a chapter there, and it's going pretty well. And it was going so well that actually the University of Melbourne wanted to start a chapter and do it there in Australia. And so I was like, sure, let's do that. And they started it, but it's sort of morphed into some other kinds of things, and so they're not really doing it anymore. Michigan State also had an administrator who was very interested in coordinating this for their biosciences people, so at ICER and Beacon. And they started it, so they got so far as to having a website and having one initial meeting, but that's as far as it went. Yale had a very excited graduate student in her third year who really wanted to start the hackathon, but ultimately it turned out that she got very busy and wasn't able to lead it all by herself and didn't really have the resources to do that. So it also failed. However, Swinburne University of Technology, also in Australia, in Melbourne, tried again. And it's actually working. So they started a chapter in the winter of last year, and it seems to be going still very strong, and they've had a number of meetings and lots of attendance, and it's everyone from undergraduates, graduates, postdocs, even faculty. And here in the University of Illinois, it just started this semester, and I think actually Erin, having been at the University of Wisconsin and seen how a hackathon group can succeed, has been doing a great job. And the thing that this brings to people is a place that's safe, because it's peers, right? They might not know everything like your professors are assumed to do. And it's also an exciting community. And so the things that I think are working in the places where it is working are community. So it's led by somewhat democratic anarchy where, because it's peer-led, the people who are the audience give the talks, right? And they're not talks, they're sort of demo-based. And if you give everyone access to push to the Git repo, they will edit the website on their own. Additionally, there should be some sort of cult-like leadership. And so, Aaron is that person here, and he's like, I got a great personality. He's, someone you want to be around. In Wisconsin, it was this guy, Malad Fatnashad. It's really important. It can be a group of people. So at Berkeley, it's this whole group of people at BIDS that attract a whole number of other people. And it's actually really important to have social events with those hacking types that you make friends with, and so occasionally we organize beer-related outings. This is the original group of people at Wisconsin, and I think that community tied us together really well, and actually a number of these people are now really well-known faces in the SciPy community. It's also peer-driven, so I talked a little bit about this, but by making the platform as peer-focused as possible, it allows people to feel safe, but it also, if you invite people from different disciplines, then it's okay to have different skill sets, and that normalizes the mixed skill levels. If there are various ecologists or biologists, they're not expected to know the same things as physicists are, and so it becomes an even more safe space to share things. Additionally, having people give talks about the things that they're interested and excited about appeals to their desire to show off. So at Berkeley, the kinds of things we've been talking about, here's a list recently. Here's our current live website of the past things that we've given at Berkeley, the people who've been teaching it. It's covered a whole fleet of things, from packaging to parallelization in both Python on GPUs, how to test your code, how to plot it, how to analyze it with all kinds of cool things. On Wednesday of this week, it was scikit image. And at Wisconsin, we also led some boot camps just to teach other people at our university. And so, we led one that was C++ focused. This was in 2009. And then we discovered something called software carpentry. We Googled it around on the internet. My PhD advisor pointed us to a video that Greg Wilson had made. So we put together a boot camp to show people this particular set of skills that Greg had been sharing with other scientists at Los Alamos and across industries. And this set of skills he felt were essential to the behavior of well-formed, robust science. And this included, the ability to deal with the shell, handle some different libraries, debug scripts, and do basic programming. This has evolved a lot, but we invited Greg, the first time I met him was we invited him to give the keynote at this, and at that time he was a University of Toronto professor and in CS. And that's changed a bit since then. We taught other things. We taught a full Python boot camp, and that was very popular. We had speakers like John Hunter give talks about Matplotlib, and these are the kinds of events that have worked really well. We had another software carpentry boot camp where we developed a bunch of materials closely related to the ones from before, and it started to look a little bit more like modern software carpentry. But I keep throwing this word around. So that's the Hacker Within. I think it's working, but it's a Band-Aid on the problem, right? No peer teaching group is going to be able to teach young scientists all the skills they need to learn to do science more effectively by the time they hit graduate school. It is also run entirely based on volunteer STEAM. And those volunteers also leave when they leave graduate school. And so continuity is a problem in these groups, and it's just a Band-Aid. So it's a great solution. It's a wonderful thing. You should come to the one at the University of Illinois here. I think it's going really well. But another solution that is a little more sustainable than this is software carpentry. So in addition to the Hacker Within, software carpentry is helping with this problem. And I'll just describe how many of you have heard of software carpentry before this talk? So it's very visible. It is a project that Greg Wilson started in Los Alamos in the 90s, a long time ago. And it was focused on scientists who have the problem of having to get their It started with scientists who needed to get their software onto a high-performance computing machine and had not the first idea of how to program. And that problem still exists today, right? It's very common. Many of you have seen it. It's getting better, but I think it's actually it's not going to be fixed until we get it into the curriculum. But software carpentry seeks to give these skills to people as a more robust Band-Aid than these peer organizations. Software carpentry is a foundation. It's held by NumFocus. It has an elected steering committee. So as Matt mentioned, I'm on that steering committee. I'm the chair of that steering committee, which means I get to help direct where it's going, and it's been extremely fun. It's also got a representative expert advisory council, so a lot of the organizations that support software carpentry, there's too many to list here. One of the most important ones early on was the Sloan Foundation, but it's included a great number of universities, national labs, et cetera, support software carpentry, and they all have representatives on our advisory council, and they're usually made up of expert scientists from across the world. And our mission is to make researchers and scientists more productive by teaching them what we call basic lab skills for scientific computing. And the premise here is that chemists learn how to use a beaker when they go to their school, their regular classes in chemistry, and that is an essential part of becoming a chemist. And today's scientists use computers in the same way that lab tools and materials and measuring instruments used to be used. They are an essential skill, and so we try to teach those skills. It looks a little more like this. So a software carpentry workshop is the method by which we convey these skills, and it looks sort of like this. This is the bid space again, and it's completely full on the afternoon of the second day of this workshop, right? It takes a lot to get people to show up voluntarily on a weekend for 2 straight days. But software carpentry is enough. And the way that it works, and one of the reasons that it's that it's extremely popular, is that it's compressed into 2 days. It gives everyone a taste of a number of different best practices. And scientists teach scientists, so it's entirely taught by volunteers. How many of you have taught a software carpentry workshop? Yeah, Matt, we've got David, we've got Neil. So you don't have to be a certified software carpentry instructor to teach a software carpentry workshop, but there must be one certified software carpentry instructor in the facility. But most people are scientists, postdocs, graduate students, et cetera. And all the materials are open access. They're on GitHub. You can fork them, change them, make them your own. And the kinds of things that we teach are very much like those Hacker Within workshops that were based on Greg's original idea. But we teach these sets of tools. So Many people choose between this latter set, and some people choose R instead of Python. It's really a 4-section course, and so most people choose between SQL and nose. But why are we teaching tools, right? We tell everyone we're going to teach them these tools they've heard they need to have, but what we're really teaching them is skills, concepts. We're not teaching Bash to teach Bash, because you can't learn that in 4 hours anyway. What we're teaching them is that there is value in automating tasks, that scripting in your file system is way easier than clicking around, and in fact, more reproducible. We teach them Python not to teach them a cool new programming language with which to do their science, because again, we cannot teach that in 4 hours. We teach them this to give them some idea of how to build code that uses the dry principle and incorporates object orientation. We use Git to track and share work. We teach them SQL to manage data, and we teach them Nose to program defensively, to insert tests into all their software. Because scientists understand tests. Like, we have whole consortia related to validation, but very few scientists actually incorporate tests into their software. So where has software carpentry been? So here's a map of all the places we've been in the last few years. And you can see there's a lot in North America. There's 182, in fact, in just the East Coast alone. And you have a lot in Europe, but we're moving further south of the equator. There's a number in Brazil and whatnot. I know you're all very curious whether there have been workshops here, and indeed there have. So here we are in Champaign, and there were two. One taught specifically for CSE and another here, so I think it was taught by these folks who were raising their hands. And so you can get to these workshops pretty easily. There are a number of them in Chicago as well. And you can see we've hit a whole fleet of countries, and this is all on volunteer power. And you can see the number of workshops that we've been teaching. This is cumulative, so the demand continues. It's not abating in the least. This green, I know these numbers are somewhat small, but the green axis on the left is the number of cumulative learners reached, so the number of people who have attended a workshop. And on the right here, we've just surpassed 500 workshops run so far. On the left, you can see we've surpassed 16,000 people who have taken a software carpentry workshop, right? All with volunteers. And our team, those volunteers, are also from everywhere. And they're made of PhD students and scientists at different national labs. You can see that there are certain concentrations in the same places where there are workshops. You have, again, a couple of people who name Illinois, Champaign, their favorite airport. So this is by airport, this map. And so there are your people. And you can see that there's a great concentration in the US, in Europe, and a few in Australia. So all of that is done by this great fleet of, actually, let me take a step back. So you can see there are a lot of faces here. I know a number of you probably recognize some of these faces as maybe scientists you've collaborated with. I know they're somewhat small, but there are some somewhat famous people here who have dedicated volunteer hours to their to this project. You can see other Moore Fellows, like Matt here is one of the Moore Fellows, the Data-Driven Discovery Fellows. There's Ethan down there. Titus is on here somewhere. But why would you bother doing such a thing? We actually surveyed a lot of people to determine this. And they do it for community, and they do it to travel. So you can actually get a flight paid for by being a software carpentry instructor to a great institution like NCSA. A place like this might fly in a software carpentry instructor if there aren't enough locally. It gives people teaching experience in things that they're interested in. And a lot of them learn from being teachers, not just the pedagogy, but also the skills. And almost entirely, all of the people who do it out of this sense of need, that this is a great challenge and a desperate issue in science, and that people really need this program to happen. And some of them do it because they're finding their graduate students aren't ready for their work, and some of them are doing it because they are graduate students who are not ready for their work. So how do we train these people? So actually, they don't just show up. Greg has a whole instructor training system built around some science-based processes and techniques for smart teaching. And these are required reading for becoming a software carpentry instructor, these books on research-based principles. It's a very science-focused set of rules for how to teach someone something and how to convey concepts. And some of the things that we employ based on this work in a software carpentry workshop is that people have their fingers on the keyboards. People are actively learning, running examples. All of the software carpentry material is in these very interactive formats like IPython notebooks. Everything is based on exercises. There are numerous helpers in the rooms because every time you have a computational workshop, there will be bugs and issues. And so we've implemented a whole suite of really interesting techniques, like we give everyone a green and red sticky note. And as soon as they have a problem, they put up the red sticky note on the top of their computer, and a helper comes and runs and helps them with their bug. And if they're doing fine or they've finished the task, they put up the green sticky note. This is a great teaching tool. It's extremely simple, and we've equipped 500 instructors with this idea, right? Scientists in their own domains now have this skill. And I think that's actually where a lot of the software carpentry value is coming in, is the training of instructors in this kind of pedagogy, which allows people to go forth, even outside of a software carpentry workshop, and use those skills for their own teaching. You can actually see this in some of the data. So here's a graph of the instructors trained over time, right? These are the people who have been trained by Greg to become software carpentry instructors. You can see there's this early edge at the beginning where a whole lot of us were informally trained by Greg, a few of us in this room included, and we're sort of automatically, we talked him through that instructor training, and it was developed alongside us, and it was an iterative process. And then once you get into May and September of 2013, we had some Sloan funding, and Greg was able to do this through Mozilla. Once we hit mid-2014, software carpentry became its own foundation. And once it became its own foundation, Greg had a job that was dedicated to software carpentry, and he was able to dedicate full-time to this kind of work. And you can see the increase of instructors that we then saw at that point, because he became very dedicated to teaching people pedagogy about scientific computing education. But something very interesting, and this is the size of our various workshops run. So you can see that as that happened, we started to see more frequent workshops. These red peaks down here at the bottom are the workshops run per day. And these tall peaks are the average size of workshop on that day. And you can see there are a few really tall ones, and that's because we've been teaching massive women in science and engineering workshops. And that require tons of instructors and numerous rooms, and they're a great blast. Right, anyway, so you can see that I was going to get to this one first, but so if you plot this cumulative instructors trained over the cumulative workshops run that we were talking about before, there is a change in the ratio right here when we start to be our own foundation. And that's because people started coming. It's because of a couple things. People who had been teaching workshops for a few years started to become professors in various locations and no longer have quite as much time to dedicate to workshops everywhere. But also people started, and this is I'm not just speculating, this is based on our discussions with these people, people started coming just to learn from Greg the pedagogy. Because, okay, so how many of you currently teach? Yeah, a handful of you. Of those of you who currently teach, how many of you have been trained to teach? Yeah, okay, so now that was like 2 out of the 6 of you that raised your hands. And a lot of people really want to know how to teach well. It's remarkable. People who have a high quality standard for their work also have a high quality standard for their teaching, right? And they want science to show them how to teach. So a lot of people have been attending this instructor training in order to get that information. So software carpentry is working. It's popular among students and learners. It's popular among institutions that are funding software carpentry. And it's popular among instructors who need to learn how to be instructors. With the final sort of 15 minutes of this, 10 minutes, I'm going to talk about what I think So those are great solutions, but they're not sustainable. I'm going to talk about what I think is the only sustainable solution and is a huge challenge. And I think it's to infuse traditional curriculum in the universities with computing. This could be its own talk, the motivations behind why computational thinking and computational learning and all of these things are essential to students today, but I'll just give you this. Today's students need computers like Galileo needed algebra, like you and I needed calculus. They need computers to speak the language of science, right? Given this fact, you will have to agree with me that in order for this to be sustainable, traditional curriculum teaching science must teach the tool that is the language of science today. And that, in addition to math, is computers. But how do we do it? What are we going to throw away, first of all? Because curriculum is full, right? There is no room for another class, especially in engineering, where ABET has a lock on all undergraduate classes. There's no way to get students to come voluntarily to something that they're not already endogenously excited about. So software carpentry has a lot of people attending, but they come when they have a need, right? Very few of them come just like because they're kind of interested in it. Most of them come because their PI told them they need to do something and they have no idea how to learn it, right? And so it really needs to be in the curriculum, and it can't overload professors, right? Professors don't have time to completely refactor every class that they've ever taught. But you can make it open source so that they could share their lessons, right? Every numerical methods class in every domain should have some open source set of IPython notebooks that walk through the numerical methods in that domain. And they should be shared and collaborated on by all the professors teaching numerical methods that semester in that domain. You shouldn't all be reproducing each other's work. You can fork it, make your own branch. It can be your own class. There's no reason for everyone to teach the same class, but you could certainly use each other's work. And I think the curriculum would improve. Also, there is a lot of research that example-driven, project-driven, exercise-focused work is much, much better for learning comprehension. So students retain things if you have taught them how to apply the concepts, right? And so if you introduce the concepts in the context of computation, then you are teaching them science in the way that they're going to use it. If it's project-focused, it has the same thing, and you can do it incrementally. You can walk them through the very basic steps over the course of a semester with an incremental project that have incremental assignments leading to a larger goal. And all of this can be in a flipped sort of active classroom because you're focused on these examples. And the tools exist, right? There are a lot of tools for teaching in this way. I'm going to give you one quick example. It's called NB Grader. And a friend of mine, Jess Hamrick, who is on the Jupyter team, has created a grading notebook tool. So you can create assignments in the IPython or Jupyter notebook, and they can be auto-graded or manually graded. So the way that this works, this is a sort of live of her documentation. But the idea is you open up a Jupyter notebook, and you have a plugin that you have to install, this NB Grader plugin, and you can create a manually graded answer cell, an automatically graded answer cell, and you can make a read-only answer cells, etc. And so you can walk people through the assignment, have them put their solutions in a cell that then is either manually graded by you later, maybe it's in LaTeX or whatever if you want them to output a math solution, or if it's a program or the result of an algorithm that they need to accomplish, then you can run tests automatically on the back end to determine the grade that they get for that solution. Maybe they get partial credit if it solves this answer, and they get full credit if it also scales, right? And so you can write unit tests for the NB Grader notebooks that then automatically grade all of your computational assignments. So this is an innovation, and it's amazing, and she's been using it in actual classes, and it's working. And I think with tools like this at our disposal, there's no reason not to create assignments in something like the IPython notebook. And there are also a lot of big initiatives, so I'm not the only one talking about this. At Berkeley, there's this initiative that we incorporate data science into the curriculum. And we can disagree or agree on what data science is or what it means, but ultimately the model that they're suggesting, and this is mostly the brainchild of people like Catherine Carson and David Kohler at Berkeley, who are generating this course content. But the undergraduate experience, it now has the option, or will soon have the option, for people to go through and major in data science, minor in data science, or have some of their courses in their actual domain simply touch on computational skills that they need for statistical and computational analysis of their particular domain. And those are called the connector courses. So these half blue squares, I know it's a very confusing diagram, but these half blue squares capture what I think is the solution to embedding computation. They are courses in the domains that have incorporated enough computation for students to come away with the computational skills they need to do analysis in their field. So right now it's the University of California, Berkeley, and this is it's called the Data Science 8. Huh.
Maybe like the minors and stuff like that.
Oh, I see what you're saying.
Who institutionally owns those?
So there is a data science program that owns the minors and the majors, runs the minors and the majors and encourages the existence of the connectors. And it does so to courses that are then held in the departments. So today's majors, that section, sort of those classes are part of the departments. So like an ecology. So a great example is Carl Bettinger, who's an ecologist. He is teaching one of these connectors in the ecology department, and it incorporates computational skills that you need for computational ecology analysis and simulation of populations and whatnot. And so he has registered his class as a data science connector, right? So this is in the piloting stage, but it's a huge initiative. They currently just have this foundations course running and a couple of the connectors started up, like Carl's course. But you can go to this website and see a little more about it. But it's very common, and in fact, one of the other things that I think are really important is there's a professor in mechanical engineering called Lorena Barba at GWU, and she has created some IPython notebooks in various fields of nuclear engineering that allow students to practice plotting and changing parameters in a model of the way that planes wiggle, right? Or similarly, she has a course on Navier-Stokes, and the Navier-Stokes is in 12 steps that she slowly walks people through a computational model of, all of the pieces of the Navier-Stokes equation, and by the end of the course, they're plotting and playing with the Navier-Stokes equation that they have implemented in the notebooks, right? And so by doing this, these students are now discovering the science through computation. They are playing with the parameters and seeing the changes that are present in the mathematical solution instantly. And she runs through these during class. She also flips the classroom, so she has videos available online of the content, but obviously is communicating the dynamic content in class. Okay, so I have one effort that I'm trying to replicate some of these ideas. We just started it, so I just wanted to introduce this as a last note and maybe like a suggestion or a challenge or a request at the end of this is that I think, so I wrote this book with my friend Anthony. He's a professor at the University of South Carolina, and it was the book that we had hoped would exist as soon as we needed to start training graduate students. Like I'm hoping to be a faculty member someday, and it contains all the things that I think a young graduate student in any of the physical sciences should know. Now, I'll just note that I know that the title restricts it to physics, but there's not actually much physics in it. There are a lot of cute physics stories and like physics-related history nuggets, and all the examples are very physics-focused. But basically, if you're in a physical sciences, or any actual kind of, there are only a couple chapters that need to be discarded if you're in something other than physics or engineering. And we wrote it because Anthony convinced me that if there is a book you want to read and it hasn't been written yet, you have to write it. And so we did over the course of the last year, and it includes a couple of features. So it has a part about getting started, and we introduced the command line and Python and essential containers, flow control, classes and objects. And this is like an extended version of the first section of a software carpentry workshop, or maybe the first day of a software carpentry workshop. And it's very, very example focused, so there are examples for everything. We then teach people, once they've gotten started, they've gotten their feet wet in programming and getting through the shell, we teach them how to get their stuff done, right? They have the data structures and the loops and stuff now, and we give them, and they have the containers and such, and we teach them more like how to deploy software and package software and perform in parallel, how to use regular expressions to search more efficiently through things and edit their data, make changes. And we teach them a few plotting tools and analysis and visualization techniques that are just very basic. And we talk about files in HDF5. And then we want to get it right? I was talking about reproducibility and objectivity and transparency. And so in order to do that, we talk about building software pipelines, workflows that can be reproduced, make files. We introduce them to local and remote version control. We talk about GitHub and collaboration. Mostly, though, we have a very long chapter on debugging and another long chapter on testing. And both of these are extremely essential. The debugging chapter goes everything all the way into profiling your code. And that section on getting it right has been extremely popular because it goes just one step further than a lot of the software carpentry workshops are capable of doing in 2 days. And I think they really get to the meat of reproducibility and such like this. And then we talk about the fluffy stuff at the end of the book, right? The fluffy stuff that really gets you going, getting it out there. If a paper is written in the forest, did anyone read it? If a piece of code is on your computer, can anyone use it? And no, and even if a piece of code is on the internet, not everyone can use it. This whole section is primarily driven by a strong open science ethic that both Anthony and I have and have been utilizing in our research. It talks about everything from licenses and copyright to how to use LaTeX and how to document your code automatically with Sphinx. It mentions other things like Doxygen if you're a C++ type. And it talks at great length about a handful of other things in the further musings chapter, which was a collector for other opinions and thoughts that we had about ideas that one should pursue in a reproducible open science world. So that's what the book has in it. And you can imagine a case where a simulation-focused course or a modeling-focused course could use this book as a framework for teaching a domain through the development of a model for science in that domain. And so we're developing a set of IPython notebooks that are open source. They're CCND by or something. I don't remember. You're not supposed to sell them. That's the only real rule. It's project-driven, so it allows you to sort of plop in a project in your domain and let people walk through that project. The in-class work is example-driven, and there are just a lot of exercises and examples in the book that allow people to run into problems with each of these tools and issues, and get themselves back out and learn pretty quickly how to do that. And the idea is we're going to have sort of a BYO science template. So a nuclear engineer might use it and add nuclear engineering science to the pieces of it, and focus it around in a more nuclear engineering focused project. But similarly, a biologist shouldn't be afraid of grabbing the notebooks and adding their science too. And so it's a work in progress, and it's currently being alpha tested by Tiffany Timbers at Simon Fraser University. She has a really intensive course on this. And we're alpha testing those notebooks right now, and we're hoping maybe next semester they'll be ready for forking and using and playing and debugging and kicking the tires and such. You can find the current work there in this seminar URL. And it looks a lot like those Jupyter notebooks that Lorena has because I admire her enormously, if you haven't noticed that. I think she may come to visit you guys someday soon, and if not, then that's really sad. But it looks like this. We teach, for example, in the testing section, we teach what a testing function looks like, and then we say, go back to your project code that you've been developing over the course of the semester and add a test, right? And you sit there and do that during class, and then go home and finish outfitting your project with more tests, and maybe seek a certain level of test coverage, or try to attack certain corner cases in your project, right? And so this kind of thing is a pretty excellent framework for any kind of project-based class. So that's all I have. I wanted to share that with you guys. I know it's not a lot that anyone hasn't thought pieces about, but I think I've thought about it a lot, and I have a pretty mature knowledge of what I think really, really needs to happen. And most of it has come from the Hacker Within and Software Carpentry. And these people, mostly, and I'm funded by these people. Here's some links. The code is online. The slides are online. So thank you so much for coming to this. I've really enjoyed my time here at NCSA. I've had some really amazing conversations. I've seen some beautiful visualizations. I've seen some really cool, discussions happening, and I just was really thrilled to come and visit you all.
Of software carpentry, and if you have seen any indications that it does improve the software skills of the students?
Yeah, we've had a number of attempts to assess the impact of software carpentry. With 16,000 learners, you would think it would be pretty easy to get a hold of a large survey of people. And it's actually a little harder than you think to get a non-biased voluntary response survey, right? Because the people who respond to a survey are often quite excited, or in either a positive or a negative way, about whatever they're being called to respond about. And so actually they've been pretty small. But we recently had one paper that's out on the archive, I'm forgetting, Alexandra something. No, not Pavlik, it's another lady. I'll remember it. I'll put it in this slide set later. But we recently had someone do some assessment through a set of surveys. And it was a very small sample size, but what she came to discover was that most people who'd gone through a software carpentry workshop felt that they were more efficient by 10 to 20% after the workshop. And many people expressed, so this was a verbally coded interview, and many people expressed that it would have taken literally forever to learn these things by themselves and to know where to look. And so that's actually a really interesting result that's mostly anecdotal, but we're looking forward to the possibility that someday we will have funding to hire someone who has the kinds of skills and training to quantitatively and robustly test our impact. And if anyone knows anyone in particular, or any opportunities in particular to fund such a thing, we are extremely interested. Yes.
In science education, how do you balance in this world with young people I know that I work with? Mm-hmm. They're so enthusiastic about information on the web, they don't research the source. So there's some assumptions, and there's assumptions about programming. How do you balance teaching students how to critically think about the computer, the computational process? How do you wrap in critical thinking around the emphasis on hacking self-driven groups that might even be teaching one another poor skills?
I think that's very valid, and it's a subtle point. I think the thing that I think about when you were saying this is, in particular, I've seen a real problem once you give people the kind of computational skills that they need to quickly produce a plot that produces some analysis. They maybe will apply it to the wrong problem, or not think hard about the parameter range for which it's valid, and that kind of thing. I think definitely can't be addressed without computation in the classroom, but with computation in the classroom, I think it has to be explicitly and continuously addressed at all times. So every time you're talking about a parameter, you need to talk about what kind of input tests and exceptions you need to throw for what valid ranges and such things. How to design a more sort of user protective software. So in the future, when people misuse software, it keeps from being. But as scientists, I think that also comes in the domain teaching, right? So when you're teaching that science, it also needs to be clear which models are appropriate for what situations. And I think that comes in, especially in example-driven teaching, if you can show that this model is unrealistic or inappropriate. I think there's a lot of opportunity for showing rather than telling this kind of thing, because you could sort of show someone how wrong they could accidentally be, and that's somewhat terrifying to the right people. Similarly, like a great motivator for reproducible science is paper retractions. How many of you just gasped, right? If your code is reproducible and your software is reproducible, you're going to be a little more robust to that kind of fear scenario. But I think that's a very good question, and I think that's something we're going to continuously struggle with. something maybe we've been struggling with science and since the beginning of models, even mathematical ones, since the beginning of time.
So your initial hacker within group seemed to be pretty gender unbalanced, and I was wondering to what extent, as as it's growing, and as the software carpentry stuff has grown, what have you seen in terms of that?
Yeah, so this is what you're talking about, and there's two of us, and in fact now it's even worse. If we can be really frank, this is Berkeley. And this individual with long hair is actually a man. His name's Sean. He's he's a kind guy. This, and this. These are the three women in the room, I believe. It's quite a large room. And I don't know. It's something I think about, probably as much as almost every single one of you thinks about diversity in science, and in particular in computational science, where there's an intersectionality problem. So intersectionality is this notion that groups that are a minority have a problem where, groups that a single person who maybe represents two minority groups in a situation. So the canonical example is like a black woman. In most situations is like a double minority in academia or whatever. This is called intersectionality. We could talk about it as, rainbow unicorns. I think as soon as you start to ask someone to not only be a female scientist, but a female computational scientist, it starts to be a smaller population. Even this very room is a very similar example. If we look around, I don't have a solution. I don't know what to do about it in terms of attracting more people. I think, you want to lower barriers and not standards, right? You want to make sure that everyone feels welcome and that, stereotype threat, so sort of like Claude Steele's stereotype threat, you want to make sure that that's not present in spaces. So I think a lot of the kinds of things that the Hacker Within attempts to do to make the safest space as safe as possible maybe help, but certainly aren't winning. I don't really know.
So it's not just scientists that are using computers now. We have digital humanists. And I wondered, what seemed to emerge out of your talk is one of the great advantages of the Hacker Within is having biologists talking to physicists, and the fact that they come from very different disciplinary backgrounds is helpful in feeling comfortable about admitting you don't know. So would it work to bring in humanities scholars as well, or should we sort of do Hacker Withins just for humanities scholars separate from scientists?
So I think that's a great idea, and I know that like Mohammed and Aaron here, who are leading the Hacker Within here in Illinois, start the session with some explanation of whatever the attendees are doing. So they'll, I guess pick someone for next week, gives a 10-minute talk on what they're doing. And I don't think you have any rules about who can come, right? In Berkeley, we do have a couple. We have a journalist and a social scientist that come sometimes. And software carpentry has had a great deal of, there's a murmur about the possibility of a library carpentry, that because librarians have this need, just like you're saying, a lot of them are digital humanists. I think that they probably feel probably doubly uncomfortable when science and arrays are thrown around and with like sort of no notion of what people's linear algebra background is, and so I think it's very valid. I would love to see them feel comfortable in a Hacker Within type space, but you're probably right that maybe they need a slightly more customized space but I also don't want to create a division. I think that's a really interesting problem that takes some maybe iteration. Maybe these guys will figure it out, because I think they're really trying to reach out to some more interdisciplinary groups and make everyone feel like they know what everyone else is doing here. Do you have any desire to say anything about that?
So hi, I'm Aaron. We have a neuroscientist that's pretty active. So with Beckman being so big and then having a lot of large studies, that's someone that's not typically thought of, at least historically, as a data scientist. So we have some there. I think PR is a little bit of a problem for us. We just want to get the word out as much as we can and make it as applicable as we can. So we don't always know what people want is a little bit of a problem, so that whoever needs something comes. And we are trying to address the gender problem. We have similar issues. And we're going to screen a documentary coming up. We were going to do it at the end of the semester, but we're likely going to move it to the beginning of the next semester just to get to a little more exposure about that problem, because we realize it's a problem and we want to do something about it. So there'll be more coming.
So let's thank Katy again.
Thank you.